Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 2, Section 1, Chapter 7, Topic 3. Understanding warpage and its significance in semiconductor packaging. Introduction. Warpage is a common phenomenon in semiconductor packaging characterized by non-uniform deformation or bending of packaged devices or substrates. It can result from various factors such as material properties, processing conditions, and thermal stresses. Understanding warpage is crucial in semiconductor packaging as it directly impacts the reliability, performance, and manufacturability of packaged devices. This overview aims to define warpage, discuss its causes, implications, measurement methods, and mitigation strategies in the context of semiconductor packaging. 1. Definition and causes of warpage. A. Definition. Warpage refers to the deviation from the intended flatness or planarity of packaged devices, substrates, or printed circuit boards, PCBs, in semiconductor packaging. 1. It can manifest as bowing, twisting, or bending of the substrate or package components, leading to dimensional inaccuracies and potential reliability issues. 1. B. Causes of warpage. I. Differential CTE. Variations in the coefficient of thermal expansion, CTE, between package materials, such as substrates, die-attach materials, encapsulants, and solder alloys, can induce thermal stress and mechanical deformation, resulting in warpage. 1. E. 1. Uneven heating, cooling. Non-uniform heating or cooling during manufacturing processes, such as solder reflow, encapsulation, or curing, can cause temperature gradients across the package, leading to differential thermal expansion and warpage. 1. E. 1. Material properties. Inherent material properties, such as stiffness, modulus of elasticity, and thermal conductivity, influence the susceptibility of materials to warpage. 1. Brittle materials, such as ceramics, are more prone to warpage than ductile materials, such as metals or polymers. 1. IV. 1. Process conditions. Variations in processing conditions, such as temperature profiles, ramp rates, and cooling rates, can impact the degree of warpage in semiconductor packages. 1. Improper process control or thermal management can exacerbate warpage issues during manufacturing. 1. Versus environmental factors. Exposure to temperature fluctuations, humidity, moisture absorption, and thermal cycling in real-world operating conditions can further exacerbate warpage in semiconductor packages over time. 2. Significance of warpage in semiconductor packaging. A. Reliability concerns. Warpage can lead to mechanical stress, strain, and fatigue in package components, compromising package reliability and longevity. 2. It can induce cracks, delamination, solder joint failures, wire bond detachment, and die cracking, affecting device functionality and performance. 2. B. Electrical connectivity. Warpage can cause misalignment or discontinuity in electrical interconnects, resulting in poor electrical contact, signal degradation, or open circuits. 2. It can lead to electrical failures, intermittent connectivity issues, and reduced device functionality. 2. C. Thermal management. Warpage affects the thermal performance and heat dissipation capabilities of semiconductor packages by altering the thermal interface between package components and heat sinks. 2. Non-uniform warpage can impede thermal conduction, increase thermal resistance, and degrade device cooling efficiency. 2. D. Assembly and testing challenges. Warpage complicates assembly processes, such as die attach, wire bonding, and encapsulation, by introducing dimensional inconsistencies and alignment issues. 2. It can lead to assembly defects, yield loss, and increased manufacturing costs. 2. Warpage also poses challenges for testing and inspection procedures, affecting test accuracy and reliability assessment. 3. Measurement and characterization of warpage. A. Optical inspection. Optical inspection techniques, such as digital imaging, microscopy, and profilometry, can be used to visually assess and quantify warpage in semiconductor packages. 3. These methods provide qualitative and quantitative measurements of package deformation, surface topography, and dimensional deviations. 3. B. Coordinate measurement. Coordinate measurement machines, CMMs, and coordinate measuring arms, CMAs, enable precise measurement of package geometry and dimensional deviations. 3. These metrology tools use contact or non-contact probes to capture 3D coordinate data and assess warpage in semiconductor packages with high accuracy. 3. C. Interferometry.
Interferometric techniques, such as laser interferometry and white light interferometry, provide non-contact, high-resolution measurement of surface deformations and profile variations in semiconductor packages.
3. Interferometers detect changes in optical path length caused by warpage-induced surface deflections and quantify package deformation with sub-micron resolution. 3. D. X-ray tomography. X-ray tomography enables 3D visualization and analysis of internal package structures, voids, and defects that contribute to warpage. 3. X-ray imaging techniques, such as computed tomography, CORT, and microfocus X-ray imaging, provide insights into package integrity, solder joint quality, and material distribution, aiding in warpage characterization and root cause analysis. Thanks for watching. Please like, share, and subscribe.